This is section 17.3, equations of motion, translation of a rigid body. In this example, we have a cart, and the cart has a total load of 100 kilograms, so this is the load. And the center of mass is located in this point, so the distance is given by these coordinates, and the height is given by 0.5 meters from the ground. Also, there is a force that is being applied, so someone is pushing the cart, and the force is 100 newtons force, and is applied at this angle, which is given by this little triangle coordinates. So the information that is given about the angle is that if this is theta, the cosine of theta is equal to 4 over 3, and the sine of theta is equal to 3 over 5. Sorry, this is 4 over 5. Okay, so we also are going to assume that the wheel doesn't have any weight and there is no friction in the cart. So of course there is friction on the wheel, so I have a wheel here. So the friction is opposed to the movement. So if this move in this direction, so that means that the friction is opposing. So friction is in this direction on the wheel, the force of friction. And if this is the shaft which is connected to the cart, so there is a rotation, but there is no friction in the shaft, so no friction. No friction is transmitted to the cart, so no horizontal force. So what are the final forces that we have? So we have the weight, and we have the normal forces, so normal at B, normal at A, and we have the force of 100 newtons, and we need to find the normal reactions. Okay, so let's proceed. So the first thing that we are going to do is the free body diagram and the kinetic diagram. So let me move here. So this will be the free body diagram, and this will be the kinetic diagram. So one is equal to the other, and the forces, I'm going to decompose the forces in the x and y direction. So we have x and y. So the 100 newtons force is divided in 2. So this is 100 multiplied by the cosine of the angle, which is 4 over 5. And the vertical component is 100 multiplied by the sine of the angle, which is 3 over 5. We also have the total weight, and if the weight is 100 kilograms, so the total weight is, the mass is 100 kilograms, so the weight is 981 newtons. And we have the normals at B and the normal at A. So on the right hand side in the kinetic diagram, so we have our center of mass, and we have the two components, so mass multiplied by the acceleration of g in the x direction, and we have mass multiplied by the acceleration of g in the y direction, which is 0 because it's not moving vertically. So this is 0. So now we can write the equations of motion. So we start with the sum of the forces in x, so which is equal to mass times the acceleration in x, and this acceleration is the acceleration of the center of mass. And so we have 100 multiplied by 4 over 5 on the left hand side, so that's the only force applied. So it's 100 multiplied by 4 over 5 equal to mass, which is 100 multiplied by the acceleration in x, which we don't know. The second equation that we have is the sum of the forces in y, which is equal to 0. So in y we have minus 100, the force applied in the handle, multiplied by 3 over 5, minus the weight, 981 newtons, and then we have the two normals, which are pointing up, so they are positive, plus NB plus NA, and that should be equal to 0. So far we have one unknown, two unknowns, three unknowns, and we have two equations. So the third equation will be the sum of the moments about the center of mass, and that should be, because it's not rotating, should be equal to 0. And so therefore what do we have? We have this MB is producing a moment which is positive with respect to is negative with respect to G, right? Positive is like that, negative is like that, due to the right hand rule. So then we have minus NB multiplied by the distance, so the distance, which is 0.4, the moment produced by A, so, and it's positive in this case, multiplied by that distance, which is 0.6, plus MB multiplied by 0.6. What else do we have? So we have this horizontal component, which is producing a negative, so is the force multiplied by this distance, and this distance is 1.2 minus 0.5, so that's 0.7. So minus 100 multiplied by 4 over 5, the force, multiplied by the distance, which is 0.7. And finally we have this vertical component multiplied by this distance. The distance is 0.3 plus 0.4, that's also 0.7. So plus 100 multiplied by 3 over 4, 3 over 5, multiplied by 0.7, and that is equal to 0. So in this equation we have the same unknowns, and okay, this is NB and this should be NA. We have the same two unknowns, so we have three equations, and we have three equations, and we have three unknowns. So that means that we can solve. So from the first one, we can solve for the acceleration in x, and so we can conclude that the acceleration in x, so this 100, this 100 and 100 cancel, so the acceleration of x is 4/5 or 0.8, and this is meters per second square. Now we have these two equations for NA and NB, and we can solve NA from 1, replacing the second one. You can check the maths, and the result will be that NA is equal to 430 newtons and NB is equal to 611 newtons. So that's the final result. So that involves solving from one equation for one NA or NB and replacing the second one and solve for the other variable, which is not much algebraic work, but you have to do some work. So there is another alternative for this problem. So instead of setting the sum of moments at G, we can set the moments at B, and so we can cancel MB. So the only thing that we have to take into account is that on the right hand side, if we are taking moments with respect to this point, we are going to have components of the kinetic moment. So let's do it in that way. So this is if we choose B instead of G. So we have that the sum of the moments at B is equal to the moment of inertia multiplied by alpha, but alpha is 0, so the first part is 0, but the second part is not 0, which is the mass multiplied by the acceleration in x multiplied by the distance. So what is this? So the acceleration in y is 0, but we have the kinetic component. So if we are taking moments at B, so we are taking moments with respect to B, we have the moment of this force, and the distance is this distance. Well, this inertial component. So the distance will be 0.5 0.5, assuming that B is that the size of the wheel is minimum, so that will be 0.5. Okay, so we have that the right hand side is mass acceleration in x multiplied by g, which is 0.5. So let me write again the equation. So the moments will be minus, let me do it this time over here. So moment over here. So we have the moment produced by the weight that before was cancelled. So that's and it's a negative moment. So it is 981 multiplied by the distance, which is 0.4, plus NA multiplied by the distance, which is 0.4 plus 0.6, so that's 1. NA multiplied by 1, and B is cancelled because it's passing through B, and then we have the moment of these two forces, these two components, which is minus 100 multiplied by 4/5 multiplied by 1.2. Okay, the horizontal component will produce a negative moment, and the distance is 1.2. And now we have the vertical one, which produce a positive moment with respect to this point. So that force is over there, and the distance is 0.3 plus 100 multiplied by 3 over 5 and multiplied by 0.3, and this is equal to the mass, which is 100, so this is the right hand side, multiplied by the acceleration, which is we already find it, that is 0.8, and multiplied by the distance, which is d, which is 1.5. Sorry, 0.5. So what is the advantage of taking the moment with respect to b? Is that in this equation the only unknown is NA. So instead of having two sets of equations, we just have one equation in which we just need to solve for NA. And once we solve for NA, we can use this other equation and solve for NB. And we should obtain the same results. So if we solve from here for NA, so we obtain that NA is equal to 430 newtons, as we did before. So you can check the math to see that it works. Okay, thank you.